Welcome back to the deep dive. Today we are taking, well, the ultimate field trip, really. Moving from the comforting known neighborhood of our own galaxy right out to the speculative edges of space-time, quantum mechanics, and just the sheer scale of the cosmos.
It's a huge scope.
It really is. You sent us a truly fascinating stack of sources outlining the biggest, most profound cosmic enigmas. I mean, questions that truly challenge our understanding of reality.
They absolutely do.
So our mission today is to unpack these intensely complex mysteries, moving step by step through the evidence, the conceptual breakdowns, and just the vast, beautiful questions they raise.
That's absolutely right. And the power of this material, I think, is that it frames these concepts not as settled physics, but as ongoing debates. It urges us, and you listening, to reason outward from the known data points to the ultimate unknowns.
Right.
Our guiding principle throughout this deep dive will be analyzing the evidence to understand not just what we've measured, but the sheer humbling vastness of what remains unanswered, whether that's pinning down the identity of an invisible force that makes up, the majority of the universe, or grappling with the startling implications of information being potentially lost forever in a black hole.
Big questions.
Huge. We are here to seek the underlying patterns and connect these seemingly disparate enigmas across the entire cosmic expanse.
Exactly. So over the next half hour or so, we're going to be exploring the unseen forces shaping our galaxy, tackling the paradoxes posed by black holes, and the nature of reality, considering the, well, radical idea of parallel universes.
Always a fun one.
Definitely. And finally, confronting the deafening philosophical silence of the Fermi paradox. So let's unpack this and start with what we thought we knew best. Our home, the Milky Way.
It's natural to look up at the night sky, isn't it? And perceive the Milky Way as this static, beautiful, sort of predictable band of light.
Familiar.
But the deeper we peer into the data, the more our research reminds us that it is a living, evolving entity full of secrets. And it starts with the very first observation that just shattered our classical understanding of how mass and movement should relate.
Okay, let's unpack this core mystery, the galactic rotation curve enigma. Right. So if you picture our galaxy as this vast, observable, spinning disk of stars, gas, and dust, Newtonian physics gives us a clear prediction. You'd expect stars farther away from the central, concentrated mass to slow down significantly.
Right, just like the outer planets orbit the sun slower.
Yeah.
Mercury zips around, Neptune crawls.
Exactly. That's what should happen.
Precisely. That's the logical expectation. However, the fundamental observation made decades ago and reinforced ever since is that stars extremely far out from the galactic center move just as quickly.
Or faster, even.
Or faster, yeah, than those stars closer in. This defies all calculations based on the visible mass, the stuff that emits light, the stuff we can actually see and measure.
So the stars, the gas.
All of it. The visible matter simply doesn't provide enough gravitational pull to keep those outer stars from flying off into space. They should be long gone.
So the immediate, inescapable conclusion drawn from the data is that there must be some kind of invisible force at play. Or, as one major theory suggests, a massive halo of mysterious substance enveloping the galaxy that we just cannot see.
And this is the substance we now call dark matter. It's providing the enormous amount of extra, unaccounted-for gravity necessary to keep the entire structure gravitationally bound.
The implication of this is just staggering, isn't it?
It really is. The calculations show that this invisible influence must outweigh all visible matter, all the stars, planets, and gas, by a factor of maybe 5 or 6 to 1.
Wow, so most of the galaxy's mass is invisible.
That's the conclusion. And astronomers look for evidence of it not by seeing the substance itself because, well, it doesn't seem to interact with light, but solely by observing its gravitational effects. We detect it through the anomalous speeds of stars, like we just discussed, and also on a much larger scale, through the dramatic bending of light gravitational lensing, as light passes through these invisible gravitational fields.
Wait, so if 85% of the gravitational mass in our galaxy is dark matter, why are we so sure it's matter? Like some kind of particle, and not just, I don't know, a modification of gravity itself? I know there are competing theories, right? Like MON.
That's a crucial point, and it absolutely reflects the ongoing debate in the sources. MOND, or modified Newtonian dynamics, does provide a good fit for specific rotation curves in some galaxies.
Yeah.
It tries to adjust the laws of physics at very low accelerations instead of invoking a new particle.
Okay.
But the overwhelming consensus still favors the dark matter particle hypothesis. And the reason is largely because of the evidence we see when we look beyond single galaxies, especially in galaxy clusters, which I think we'll get to later.
Right, the bigger picture.
Exactly. Dark matter works as the standard model because it satisfies phenomena on the scale of the entire cosmos, not just individual galaxies.
Mm.
It solves the rotation curve problem, sure, but it also explains how the large-scale structure of the universe, the cosmic web, formed in the first place.
Okay, that makes sense. Now, here's where it gets really interesting because we move from this vast unseen halo to the violent hidden heart of our galaxy. What exactly resides at the Milky Way's very core, hidden behind all that dust and gas?
Yeah, deep in the center, the research confirms the existence of Sagittarius A as GRA for short. It's a supermassive black hole
Supermassive.
concentrating about 4 million times the mass of our sun into a region smaller than Mercury's orbit around the sun.
That's incredibly dense.
It dramatically warps space-time right there at the galactic center.
And the proof of its existence isn't just inferred, right? It comes from actual observations, painstaking ones.
Astonishingly precise long-term observations, yeah. Specifically, tracking the orbits of stars whipping around that central point at speeds up to thousands of kilometers per second.
Just whipping around.
The sheer velocity and the tight elliptical paths required for those stars to stay in orbit indicate an immense gravitational pull from an invisible source. And the only thing that fits is a supermassive black hole.
Okay.
Furthermore, we observe activity fuel around it, though the black hole itself is dark, obviously.
You can't see it.
Right. But the surrounding accretion disks, this swirling matter, gas and dust, spiraling inward release, tremendous amounts of energy and radiation. They heat up to millions of degrees due to friction as they fall in.
And that's what we detect.
That process lights up the core in ways we can detect, primarily using radio telescopes, because visible light gets blocked by all the intervening dust. The pattern of flares and radio emissions gives us this dynamic view of this incredibly powerful engine at the galaxy center.
But the Milky Way wasn't just born like this, in this pristine state. It's grown over time through what the sources evocatively call cosmic cannibalism.
Yeah, it's a great term. This idea suggests our galaxy was essentially built piecemeal, consuming and merging with smaller dwarf galaxies over cosmic time.
So it's a galactic predator?
In a way, yes. That history of mergers is crucial to understanding our current structure. When a smaller galaxy plunges into ours, it's a chaotic process, spans hundreds of millions of years. It disrupts the stars and leaves behind these predictable, extended streams of stellar debris, like galactic scars.
And we can see those scars.
We can. We spot them through unusual groupings of stars scattered far from the main disk, all sharing remarkably similar ages, compositions, and, crucially, orbital paths. They're moving together, remnants of something that was torn apart.
And we even have a specific, vivid example detailed in the analysis, the mention of the Gaia Sausage Enceladus event, or GSE.
Quite a name.
That name evokes the chaos of a long-ago collision, maybe dating back 10 billion years, a massive event that contributed a significant amount of the Milky Way's current stellar halo.
Indeed. The GSE collision was so profound, it dramatically thickened the disk of our galaxy and added enough energy to the stars to create those characteristic stellar streams we were just talking about. It confirms the Milky Way's history as a celestial cannibal that has grown through violence.
And this chaotic history leads us right back to the nature of dark matter, doesn't it?
It does, in a really interesting way. Those stellar streams, they aren't perfectly smooth ribbons of stars. They often show peculiar features like spurs, ripples, gaps even.
The dark clumps idea.
Exactly. The leading theory is that dense, smaller clumps or subhalos of that invisible dark substance are actively perturbing the paths of these stars as they orbit. They act like gravitational ghosts tugging on the stellar streams.
So dark matter isn't just a smooth halo, it might be lumpy.
It suggests that the dark component might not be uniform and smooth, as initially modeled, but rather clumpy and highly dynamic. Maybe it even has unique self-interacting properties we haven't yet discovered. This observation turns dark matter from just a simple uniform halo into a complex, textured gravitational landscape.
Fascinating. Beyond structure, there are other galactic anomalies that continue to puzzle astronomers and challenge our instruments. I'm thinking specifically of the space roar.
Yes, the arcade discovery. This persistent, low-frequency background radio noise detected by instruments, which is far louder, about 6 times louder than expected, based on all known astrophysical sources like distant galaxies or even normal star formation within our own galaxy.
6 times louder. Where's it coming from?
That's the challenge. It's immense. Distinguishing whether that noise is some kind of echo of countless stars forming locally, sort of nearby, or if it's coming from something much more exotic and distant, maybe from the very first stars ever formed. It complicates our search for fainter signals we were looking for, like signals from the cosmic dawn.
And structurally, even the everyday look of our galaxy holds fundamental puzzles, like the spiral arms. We still ponder the driving mechanism behind the galaxy's distinctive spiral arms, right?
Absolutely. Are they fixed physical patterns of material, like beads on a string? Or are they ephemeral density waves?
Density waves, like traffic jams.
Exactly like traffic jams in space, where material bunches up temporarily, sparking star formation before moving on. The waves pattern persists, but the stars and gas flow through it.
Okay.
The density wave theory is powerful, but we also have to account for the crucial role of the galaxy's central bar-shaped bulge. This bar is a vast, elongated structure of stars that rotates as a unit.
And it does what?
It's theorized to act like a gravitational steering mechanism. It helps drive the spiral arms by funneling gas inward towards the central supermassive black hole, feeding it.
Right.
So all these elements, the dark halo, the violent core, the chaotic merger history of the structure, force us to view the Milky Way not as a static backdrop, but as this vast, constantly evolving entity whose history is written in the orbital paths of its stars and the invisible stuff holding it all together.
Okay, so if dark matter is necessary to hold our galaxy together, then the research points out that the same gravitational glue must be doing the same job for, well, billions of other galaxies out there.
That's the crucial universality of it.
As we stretch our minds beyond the Milky Way, we find that same universal dark glue is everywhere, defining the structure of the entire cosmos.
Exactly. The fact that we find the identical rotation problems in essentially every single spiral galaxy we observe highlights that the same mysterious substance pervades all of them. It's what allows this unseen component to cluster gravitationally, forming the large-scale structure known as the cosmic web.
The cosmic web, it really does sound like something out of science fiction. Can you paint a picture of that?
It's truly the largest known structure in the universe. Imagine vast sheets and long, winding filaments made of galaxies and dark matter.
Like threads.
Like threads, yes, connecting dense clusters at the intersections. And these structures are separated by enormous, almost empty regions called voids.
Empty spaces.
The sources detail that the dark component essentially formed the gravitational scaffolding first, very early in the universe's history. Normal matter, like gas and dust, then fell into these deep dark matter potential wells, lighting up the filaments and eventually forming the galaxies we see today within those structures.
So the universe isn't just a random soup of galaxies. It has this underlying architecture.
It's highly structured, yeah. Not uniform at all.
And just as our galaxy has a supermassive but relatively quiet center right now, we look outward and see other galaxies with these blazing cores known as active galactic nuclei or AGNs and quasars. These things are just overwhelming in their energy output.
They can be staggeringly bright, sometimes outshining the combined light of hundreds of billions of stars in their host galaxy. It's almost unbelievable.
Where does all that energy come from?
The fuel source is identical to our own SGRA, just on overdrive. Supermassive black holes actively devouring matter at incredible rates. They achieve this blinding brightness by converting the gravitational energy of the infalling matter into radiation with astounding efficiency.
More efficient than nuclear fusion.
Much more efficient, actually. And they often eject these powerful jets of plasma at near-light speeds, extending millions of light years out into intergalactic space.
Wow. But what's fascinating here is the sheer variability. Why do some galaxies host these violent active centers, while the vast majority, including our own right now, are, well, quiescent? Sleeping giants.
It likely speaks to different evolutionary stages and maybe their local environment. AGNs need a fresh supply of gas and dust to fuel the black hole.
So they need food.
They need food, exactly.
Yeah.
A major theory is that galaxy mergers or close interactions trigger these periods of intense activity. They dump huge amounts of fuel gas and stars into the central region, feeding the beast.
And then it quiets down.
Eventually, yeah. Once the fuel supply is exhausted or maybe blown away by the powerful jets the AGN itself creates, the core turns quiet again. So the presence or absence of an AGN is like a snapshot of the galaxy's recent history of interactions or feeding events.
Okay. Moving on to galaxy collisions themselves, the sources detail what happens when two galaxies merge. It sounds cataclysmic, but you mentioned earlier it's often described as more of a graceful process of reorganization, at least for the stars.
It is reorganization, mostly, not total destruction for the individual stars. The stars themselves generally pass harmlessly by one another. Why? Because the distances between stars are just so vast compared to their actual size. It's mostly empty space.
Right. Lots of room.
But the immense gas clouds that fill the galaxies do smash together violently. That collision leads to intense compression and triggers a phenomenal surge in new star formation, what we call starbursts.
And that explains some weird galaxy shapes.
It helps explain peculiar shapes we see, yeah, like distorted spirals, galaxies with long tidal tails, or even ring galaxies that are clearly still in the process of recovering from a violent interaction millions or billions of years ago.
But the single most critical piece of evidence supporting the existence of that separate, weakly interacting dark component, the dark matter particle idea, comes from one specific observation: the bullet cluster. You said this is the cornerstone.
This is truly a textbook example, and yeah, we really must spend time on it because it's so compelling. The bullet cluster consists of two colossal galaxy clusters that have recently passed through each other. A cosmic smash-up on the grandest scale.
Okay, so two huge clusters collided. What did we see?
What astronomers observed was a complete spatial separation of different kinds of mass. We use X-ray telescopes to map the visible matter, specifically the hot, glowing gas that actually constitutes the bulk of the cluster's normal baryonic mass.
The gas clouds.
Right. This gas gets slowed down and heated up dramatically by friction during the collision, essentially like a giant shock wave. It forms these distinct bullet-shaped clouds trailing behind the main clumps of galaxies.
Okay, so the normal matter slows down. Then what about the total mass?
Exactly. Then we use gravitational lensing techniques, how the cluster's gravity bends light from background galaxies to map the total gravitational pull, which tells us where most of the mass actually is, visible or invisible.
And what did that show?
What we found was that the gravitational center of mass, which must be dominated by dark matter, because that's where most of the mass, passed right through the collision without slowing down or interacting with the gas or itself very much at all.
It just ghosted through.
It remained ahead of the visible X-ray gas clouds. This strongly, almost irrefutably, suggests that the invisible dark component interacts primarily, maybe only, via gravity. It passes right through itself and through normal matter with hardly any effect.
So it can't just be a change in the laws of gravity because the gravity stayed with the invisible stuff, separate from the normal stuff.
Precisely. It acts like a separate substance. That's why the bullet cluster is such powerful evidence for particle dark matter over theories like MOND.
Okay, that's very clear. And these collisions and mergers leave behind some really exotic galaxy types that challenge our existing evolutionary models, showing us the variety of outcomes.
Definitely. Take the ultra-diffuse galaxies, or UDGs, for example. They are incredibly vast in physical size, some as big as the Milky Way in diameter, but contain very few stars, making them incredibly dim and faint, almost like ghost galaxies.
So big but nearly empty. What's the puzzle there?
The puzzle is that they appear to have roughly the same amount of dark matter as a normal galaxy of their size, but it's spread out, and somehow they didn't form many stars. Do they lack the gas density needed for normal star formation? Or are they simply holding onto their dark glue in some unexpected way? We're still figuring them out.
Then you have the fascinating jellyfish galaxies. They look like jellyfish.
They really do. These are galaxies moving very rapidly through the dense hot gas, the intergalactic medium that exists within a galaxy cluster. As they plunge through this medium,
Like swimming through water.
exactly, the pressure of this cosmic plasma, we call it RAM pressure stripping, forces the gas and dust out of the galaxy itself, leaving behind these long, trailing tentacles of star-forming material that look exactly like a jellyfish's tentacles. These observations challenge our traditional need categories of galaxy shapes and really show how crucial the environment is in dictating how a galaxy evolves.
And on the largest scale, we look at the voids. You mentioned these enormous empty spaces between the filaments of the cosmic web. Just nothingness.
Pretty much, spanning hundreds of millions of light years. It raises the question of distribution and expansion. Why are these voids so incredibly vacant?
Yeah, why?
Well, the source material suggests a couple of possibilities. Maybe the expansion of the universe itself is happening faster in these underdense regions, effectively pushing everything else away and accelerating the emptiness.
Stretching them out.
Or perhaps it goes back to the very beginning. The initial seed fluctuations of density right after the Big Bang might have just been smoother, less dense, in those regions to start with. And then gravity, over billions of years, has amplified those tiny differences, pulling matter out of the voids and into the filaments, leaving truly empty zones behind.
So it all connects back.
All these external observations reinforce the concept that galaxies don't exist in isolation. They form and evolve within this vast structure, the cosmic web, which itself is a large-scale pattern, ultimately seeded by tiny quantum fluctuations in the Big Bang's aftermath.
We've established that black holes are the engines of galaxies, these supermassive ones. Now, let's dive into these gravitational abysses themselves. Let's start with their formation and growth mechanisms. You mentioned stellar versus supermassive.
Right, we fundamentally distinguish between stellar black holes, which are relatively common, we think. They form when a single massive star, much bigger than our sun, collapses under its own weight after it runs out of nuclear fuel. It's a catastrophic core implosion.
Makes sense. Big star dies, leaves behind a black hole.
Relatively straightforward, yes. We see the progenitor stars sometimes. But the real puzzle, as the research highlights, is with these supermassive black holes, like the one in our galaxy center, SGRA. How did they grow so massive so quickly in the very young universe?
That's the mystery. They shouldn't have had enough time.
Precisely. We observe fully formed supermassive black holes, billions of solar masses, just a few 100 million years after the Big Bang. This time frame seems far too short for them to grow just by slowly accreting gas or merging with stellar black holes using standard models.
So how could it happen?
Well, the possibilities include correct. Once matter or light crosses that boundary, it cannot escape the gravitational pull. And from an outside observer's perspective, something really strange happens to time for anything falling in.
Time dilation.
Extreme gravitational time dilation. Time dramatically slows down relative to the outside universe.
And inside that horizon, the singularity.
Inside, according to general relativity, everything is inevitably forced toward the singularity, a point of theoretically infinite density and zero volume at the very center, where all the mass resides.
Infinite density. That sounds problematic for physics.
It is. This point is precisely where classical physics, particularly Einstein's general relativity, breaks down completely. The equations yield nonsensical infinities. It signals a desperate need for a more fundamental theory, likely a theory of quantum gravity.
Quantum gravity, the unification of the very big and the very small.
Exactly. A theory that successfully reconciles gravity with quantum mechanics is needed to understand what truly happens at the singularity and resolve that breakdown.
This inherent breakdown leads us directly to one of the biggest conflicts in modern theoretical physics, the information paradox. You mentioned this earlier. It's a head-on collision between two of our most successful theories.
The conflict is stark, and quite profound. Quantum mechanics, which governs the microscopic world with incredible precision, requires a fundamental principle known as unitarity.
Meaning?
Meaning that information, essentially the unique properties that define a particle or system, its quantum state, must always be conserved. It can be scrambled, hidden, rearranged, but it cannot be truly destroyed or erased from the universe.
Okay, information must survive. But relativity says?
Well, general relativity suggests that matter falling into a black hole gets crushed into the singularity, effectively erasing its history and its unique information, leaving only the black hole's total mass, charge, and spin behind. That's the no-hair theorem.
So the information is gone?
That's the implication. And it gets worse when you consider Hawking radiation, the idea that black holes slowly evaporate over immense timescales. If the black hole disappears and the information fell inside, where did that information go? If it's truly lost forever, then quantum mechanics, as we understand it, fundamentally breaks.
That's a huge problem. So how do theorists attempt to reconcile these two opposing fundamental views without just discarding either general relativity or quantum mechanics?
It's one of the biggest challenges. The sources detail a few highly speculative but really essential attempted resolutions. One builds on Stephen Hawking's work on Hawking radiation itself.
Okay.
The theory posits that black holes slowly evaporate over eons by emitting particles due to quantum fluctuations right near the event horizon. The crucial, unanswered question is whether this radiation, which initially seems to be purely thermal random noise, somehow manages to carry the lost information out with it in some incredibly complex, encrypted way.
So the information escapes, but hidden in the radiation.
That's one hope. The mechanism is far from understood, but it's a possibility.
And the second, more conceptually radical resolution involved holography. You mentioned this too.
This is truly mind-bending. It's the holographic principle applied to black holes. The idea is that all the information about the three-dimensional interior of the black hole, everything that fell in, is somehow encoded onto the two-dimensional surface of its event horizon.
Like a hologram, a 2D surface storing a 3D image.
Exactly like that. Imagine the chip on your credit card holding vast amounts of data defining something much more complex. If this is true, then the information isn't destroyed when something falls in. It's simply stored, imprinted on the surface area.
And then?
Then, as the black hole evaporates via Hawking radiation, that radiation can effectively read the information off the surface and carry it away, preserving quantum unitarity. The information gets out.
The idea that the universe could be intrinsically holographic, that our 3D reality could be encoded on a 2D boundary, that's a profound conceptual leap.
It absolutely is. It might hint at a much deeper structure to space-time itself.
But black holes also introduce more immediate, practical, temporal and ethical quandaries for any potential space explorer, just due to that time dilation effect.
Time dilation isn't science fiction. It's a physical reality dictated by general relativity. If you were to orbit a black hole at a stable, close distance, time for you would slow dramatically relative to observers far away on Earth, say.
The source material uses that stark example, minutes passing for the explorer near the black hole.
While decades, maybe even centuries, could pass for everyone back home.
The sheer scale of that time difference, a fundamental separation of realities, would create immediate and profound ethical dilemmas, wouldn't it?
Absolutely. Should a mission even proceed, knowing the crew will effectively lose their entire world, returning to a future utterly different from the one they left? It changes the calculus of deep space exploration from purely a technical challenge to a deep philosophical and ethical one.
Yeah.
And we shouldn't forget the incredible advances we've made in actually detecting black hole events now. The source material mentions the evidence of black hole mergers, detected by sensitive instruments like LIGO and Virgo.
Gravitational waves.
Exactly. When two black holes spiral into each other and collide, space-time itself rings like a bell, sending these ripples, gravitational waves across the cosmos at the speed of light. Detecting these waves lets us hear the collision.
And what do we learn?
They reveal crucial data about the black hole's masses, their spins, how they merged, and even confirm some of the most exotic predictions of general relativity in extreme environments. It's a whole new way of observing the universe.
And despite all this knowledge, we still have mysteries, right? Like intermediate black holes. They should exist, but seem hard to find.
That's right. They should bridge the size gap between the stellar ones, a few times the sun's mass, and the supermassive ones, millions or billions. We expect them, but definitive detections are rare. Could they be hiding in the dense cores of globular clusters? We're looking.
Or primordial black holes?
Or perhaps the most ancient and provocative mystery. Primordial black holes. These are hypothetical black holes possibly formed not from stars, but in the extreme pressures and densities of the Big Bang itself, fractions of a second after the start.
And if they exist.
If they are abundant and have the right mass range, they could theoretically be the dark matter substance we've been discussing all along, made of normal stuff, just locked away very early on.
So many possibilities. Black holes constantly challenge our concepts of causality, density, information, and time itself.
They really sit at the nexus of all the deepest questions.
Okay, we've established that dark matter seems necessary within galaxies, and black holes push physics to its limits. But what if the very quantum fabric of reality extends far beyond our observable universe? This brings us to the quantum foundation of parallel universes. This is where we really shift from gravity into, deep speculation, rooted in particle physics.
It is speculative, but it originates from a real puzzle in the quantum world, which is inherently probabilistic. Particles, before they're measured, exist in a state of superposition. They can be in multiple states or locations simultaneously. Think of an electron being potentially here and there at the same time.
Until you looked.
Until an observer makes a measurement. Then somehow, this wave function, this cloud of possibilities, instantaneously collapses into one single definite outcome. We only ever see one result. The deep question is, why? Why does reality settle on just one possibility out of many?
And the many worlds interpretation, MWI, offers a radical answer to that why.
It's probably the most straightforward, mathematically speaking, though philosophically challenging. MWI suggests that the measurement doesn't collapse the possibilities at all. Instead, all possible outcomes actually happen.
All of them? How?
The universe itself branches, splits into separate, non-communicating realities or parallel universes. In one universe, the electron is here. In another, identical universe, it's there.
So if I chose coffee over tea this morning...
According to MWI, yes. Another entire you branched off at that moment and exists in a parallel universe, happily sipping tea. Every quantum choice, every decision point potentially spawns countless new realities.
Wow. Okay, that raises immediate philosophical implications about identity, free will.
Absolutely. If every single choice, every quantum fluctuation spawns a new reality, does free will truly persist in the way we traditionally understand it? Or is it more like we just experience one path through an infinite garden of forking paths, where every path is realized somewhere? It fundamentally challenges our perception of a unique self making singular choices.
It's a lot to take in, but the multiverse isn't just presented as quantum weirdness in the sources. It's also connected to the vast scale of the cosmos through concepts like eternal inflation and the cosmic landscape.
That's right. This ties directly back to the universe's very rapid expansion phase in its infancy, just fractions of a second after the Big Bang, known as cosmic inflation.
The period that smoothed everything out.
Exactly.
Yeah.
Research suggests that if inflation didn't stop uniformly everywhere at the same time, it could have continued indefinitely in remote regions of space, far beyond what we can observe.
Still inflating out there.
Potentially. This ongoing process might constantly create countless bubbles of space-time. Each bubble could detach, inflate, cool down, and become its own separate universe,
A bubble universe.
potentially possessing its own unique set of physical laws, fundamental constants, maybe even different numbers of dimensions. A vast cosmic landscape of possibilities.
And this idea leads us directly to trying to solve that great cosmic quandary, the fine-tuning problem.
Ah, yes.
Yeah.
Our universe appears incredibly, almost impossibly fine-tuned for the existence of life as we know it.
How so?
The fundamental physical constants, things like the strength of gravity, the mass of the electron, the ratio of the electromagnetic force to the strong nuclear force, they seem perfectly calibrated. If you were to tweak their values even slightly, by tiny amounts,
What would happen?
stars couldn't form, or they'd burn out too quickly, atoms wouldn't hold together, chemistry wouldn't work. Life, certainly complex life, would be completely impossible. So the question is, why are we so lucky? Why does our universe have these just right Goldilocks conditions?
This seems too convenient.
It does look fine-tuned for our existence.
Yeah.
The multiverse theory offers a potential statistical explanation. Rather than invoking design or sheer luck, it uses the anthropic principle,
Which is
which basically says, if there are an infinite or just unimaginably huge ensemble of universes, this cosmic landscape we mentioned, all with different physical laws and constants generated randomly, then by sheer statistical probability, some of them are bound to have the exact, perhaps improbable, combination of constants needed for stars, planets, chemistry, and eventually life to exist.
And of course, we find ourselves in one of those universes.
Naturally. We could only exist in a universe capable of producing observers like us. It shifts the burden of explanation from a question of why these specific laws to we live in one of the universes where life was possible. It's an explanation based on selection bias within a larger multiverse.
That seems, well, maybe like a statistical cop-out to some. Are we just left to ponder this, or is there any hope of actually searching for the unknowable, for evidence of other universes?
It remains largely speculative, and that's really the limit of the science here. It's hard to test empirically. However, the sources do mention the intriguing possibility of finding indirect evidence,
Like what?
like searching for anomalies, maybe patterns or bruises in the cosmic microwave background, CMB radiation, that faint afterglow of the Big Bang.
Bruises. From what?
Potentially from gravitational tugs or even physical collisions with other bubble universes in the very deep past, when things were perhaps closer together. Detecting such a signature would be revolutionary, but it's a long shot, and interpretation would be difficult.
So it highlights the limits of science.
It really does. If these other universes are completely isolated, causally disconnected from ours, can the multiverse hypothesis ever be truly empirically testable? Or must it remain a fascinating, perhaps mathematically necessary, but ultimately speculative explanation for why our own universe looks the way it does?
A question for the philosophers, as much as the physicists, maybe?
Perhaps.
Okay, before we leave this vast cosmic scale, we have to quickly reiterate the two greatest cosmic puzzles that underpin so much of this: dark matter and dark energy. They are the twin elephants in the room.
Absolutely. Together they make up something like 95% of the total mass energy budget of the entire universe. Yet they remain effectively invisible and profoundly mysterious. We only know them by their gravitational effects.
So dark matter, as we've established, acts like the cosmic glue, holding galaxies and galaxy clusters together. But its actual nature remains unknown.
Completely unknown. The sources outline the leading candidates being searched for. Is it composed of relatively massive, slow-moving particles like WIMP's weakly interacting massive particles? These would be heavy particles, relics from the early universe that interact only via gravity and maybe the weak nuclear force, making them incredibly hard to detect directly.
And the alternative?
Or could they be incredibly light, almost massless, hypothetical particles like axions, or something else entirely? The entire field of experimental particle physics is racing to detect these potential non-interacting ghost particles in deep underground laboratories shielded from other cosmic rays.
Still searching. And then there is dark energy, which isn't pulling things together, but actively pushing them apart. It's causing the universe's expansion to accelerate. That was a truly revolutionary discovery, right?
It was a complete shock around the late 90s. It won the Nobel Prize. The expectation based on gravity was that the expansion should be slowing down, perhaps eventually reversing in a big crunch. Instead, it's speeding up.
Why? What is dark energy?
The simplest explanation, mathematically, is the cosmological constant and intrinsic energy density of empty space itself. Something Einstein actually proposed long ago, but later called his biggest blunder.
But he might have been right, after all.
He might have been, yes. However, some sources suggest it might not be constant. It could be a dynamic energy field that changes over time, perhaps something nicknamed quintessence.
And why does that matter?
Understanding the true behavior of dark energy, if it's constant or variable, is crucial because it will determine the ultimate fate of the universe. Will it be continued expansion, cooling, and eventual darkness? Or maybe even a big rip, where the acceleration becomes so strong it tears apart galaxies, stars, planets, even atoms themselves?
Heavy stuff. And finally, this entire conversation just spirals back to the ultimate origin question. Before the Big Bang, what was there? Was it truly an infinitely dense singularity, as simple models suggest? Or was it perhaps a bounce from a previous contracting phase, part of a cyclic universe? Or could the Big Bang itself be viewed as the birth of our particular bubble universe within a larger, eternally inflating multiverse?
These puzzles are all deeply interconnected. They demand a holistic view of physics, likely involving quantum gravity that we just don't possess yet.
Okay, switching gears dramatically, but still thinking about the vastness. With the universe so immense, teeming with billions of stars, and now we know likely billions of potentially habitable planets, the research forces us to confront the most enduring existential question. Where is everybody? This is the Fermi paradox.
It's a classic and deeply unsettling question. The paradox, first famously articulated by physicist Enrico Fermi, is defined by the profound, deafening silence from the cosmos.
Explain the core conflict again.
Based on the sheer number of possible habitats out there, billions of stars in our galaxy alone, many with planets in the habitable zone. Based on the age of the universe, which is billions of years older than Earth, providing plenty of time for advanced civilizations to have developed. And based on the potential speed of exponential growth and colonization, even at slow speeds, a civilization could cross the galaxy in millions of years, a blink in cosmic time.
Yeah.
Intelligent life should be abundant and obvious. We should see signs of it everywhere.
But we don't.
But we don't. No signals, no probes, no megastructures, just silence. Why? Where is everybody?
The prevailing explanations often fall under the umbrella of the great filter theories. These are like hypothetical barriers or challenges that prevent life from reaching the stage of becoming easily detectable across interstellar distances.
Exactly. The filter could lie in our past, or it could lie in our future.
Okay, so if the filter is behind us,
that implies life rarity. The argument here is that the steps required for life to emerge in the first place, or perhaps for complex life to evolve, are far more complex and improbable than we currently realize.
Yeah.
Maybe the jump from non-living chemistry to simple self-replicating molecules is incredibly hard.
The origin of life itself.
Or maybe the jump from simple microbial cells to complex multicellular life with intelligence is the bottleneck. We search for those basic conditions now: liquid water, organic molecules, energy sources, and we're looking in extreme environments right here in our solar system, like the subsurface oceans on icy moons like Europa or Enceladus, trying to understand just how hard or easy life's start truly is.
Okay, that's one possibility. Life is just incredibly rare. But what if the filter is ahead of us?
That's perhaps the most worrying scenario: self-destruction. So the theory here suggests that civilizations tend to advance technologically only to develop the capability to destroy themselves before they achieve stable interstellar travel or communication.
Like what?
Think uncontrolled advanced AI, runaway nanotechnology, genetically engineered pandemics, nuclear war, catastrophic resource depletion, or irreversible climate change. The challenge is surviving our own technological adolescence. Maybe very few, or none, make it through.
A sobering thought.
Very. Alternatively, maybe advanced civilizations are out there, but they simply choose to be quiet, or we're looking for the wrong signs. Perhaps interstellar colonization is fundamentally unnecessary or too resource-intensive. Or maybe they recognize the ethical implications of interfering with developing worlds, creating a kind of galactic zoo scenario where they observe us but deliberately do not interact. Or perhaps their technology is so advanced, it's simply unrecognizable to us as artificial.
This uncertainty really influences our search strategies, doesn't it? We've moved beyond just passively listening for radio signals.
We have. We are now actively looking for biosignatures. This involves analyzing the light passing through the atmospheres of exoplanets. We're looking for imbalances in atmospheric gases that can't be easily explained by geology or non-living chemistry.
Like oxygen and methane together.
Exactly. On Earth, that combination is a strong sign of biological activity. Finding that on an exoplanet would be huge, though still not definitive proof of intelligence. This atmospheric analysis with telescopes like JWST is a primary near-term strategy.
And then there's still SETI, the search for extraterrestrial intelligence, which traditionally focused on radio signals. But the speculation in the source material is captivating. What if advanced civilizations use completely different mediums we haven't prioritized?
Right. Maybe powerful optical lasers for communication. Or perhaps signals sent via neutrinos, which are incredibly hard to detect. Or even using gravitational waves somehow. Our assumptions about communication might be too anthropocentric.
Or what if, as some research suggests, they're lurking closer than we think? Maybe ancient autonomous probes placed in our own solar system millennia ago, just watching.
That's the lurker hypothesis. It's highly speculative, of course, but not impossible to test in principle. We are starting to scan the solar system for anomalous objects more systematically.
It all comes back to the Drake equation, doesn't it? Trying to estimate the number of civilizations.
Yes, but the Drake equation has so many unknown factors, like the fraction of planets where life arises, the fraction that develops intelligence, the average lifespan of a communicating civilization, that tweaking any of them results in estimates that vary wildly from millions of civilizations in the galaxy right now down to essentially just us. It remains more of a framework for thinking than a precise calculation.
And this uncertainty leads us inevitably to the ethics of contact. If we did detect a signal, or if we consider sending our own, should humanity actively seek contact, or should we perhaps remain quiet, mindful of the potential dangers?
There is a serious risk versus reward calculation here, and it's something we need to address conversationally as a species, really. Stephen Hawking famously warned that advanced civilizations might not necessarily be benign or altruistic.
Right, the colonization fear.
They might view us as primitive or see Earth's resources as something to be exploited. Contacting them could be, in his view, profoundly dangerous for humanity. This fuels the ongoing debate between passively listening, SETI, versus actively transmitting powerful messages out into space, messaging extraterrestrial intelligence.
Yeah.
Should we shab into the jungle, or just listen carefully first?
For now, the universe seems silent. It leaves us only with the hope, the mystery, and maybe the fear that the Fermi paradox inspires. The ultimate question hangs there. Are we profoundly alone in this vast cosmos, or perhaps profoundly insignificant in a crowded one?
It's one of the biggest questions we can ask. #TagOutro.
We have taken a truly tremendous journey today. We've moved from the invisible dark matter holding the Milky Way's spiral arms in place, all the way out to the astonishing density inside black holes, and considered how the apparent fine-tuning of cosmic constants might only be explained by the sheer, mind-boggling number of parallel universes.
Right.
What's really clear is that all these cosmic mysteries, from the smallest quantum scales to the largest structures, are profoundly interconnected. They seem to demand a synthesis, maybe a revolution in physics, combining quantum mechanics and relativity in a way we haven't yet achieved.
Indeed. I think the final takeaway from all this is that confronting questions that so fundamentally challenge our intuition, like infinite density or invisible matter making up most of reality, or realities branching off with every choice, it requires critical thinking and, importantly, intellectual humility above all else.
Yeah.
The universe reveals itself in subtle patterns and sometimes startling anomalies that force us to constantly question our core assumptions about reality, about the laws of physics, and even about our own place within this vast, intricate cosmic web.
The universe truly awaits discovery, and it feels like the biggest discoveries often lie in the places we can't yet see or easily comprehend.
Exactly. And reflecting on the complexities we covered today, especially that idea of the information paradox and black hole holography, I want to leave you, the listener, with one final provocative thought to mull over.
Okay.
If the two-dimensional surface of a black hole can indeed encode all the information about its three-dimensional interior via holography, thereby potentially resolving the paradox and flattening existence onto a boundary, how might that radical idea reshape our understanding of reality itself on a grander scale?
You mean beyond black holes?
Yes. Could the physical laws, the very substance of our entire observable universe, somehow be encoded on some vast, distant, lower-dimensional boundary surface? Think about it. What other cosmic surfaces, perhaps the edge of the observable universe itself, or even the boundaries between those hypothetical bubble universes in the multiverse, might be secretly holding hidden information about existence that we just haven't yet figured out how to read?